probably needs no introduction, is the guy whose last name you really don't know, no one knows how to pronounce. It's Szczys. It's a managing editor of Hackaday.com, Mike Szczys.
Thank you, Alec. It's a pleasure to be here. Just my second time in Europe, and I got into Belgrade yesterday. We went out and had a great time with the casual hangout. A ton of people showed up. Thank you so much for that. Stayed out way too late and giving the first talk. So it's the right way to do it. So far, it's been a whirlwind. One of the things I'm really excited about is that we have a fantastic hardware badge that Voja and Tonish developed for the conference. Embedded systems are one of my favorite things to play with, and I had a lot of fun working on the C framework for this. And when we started talking about this, I started looking around at other projects, what other people were doing, what this chip was being used for, and I kept coming across this argument in comments on posts about 8-bit versus 32-bit families and the virtues of those. I actually started off getting into engineering through building beam robots, and just little simple robots that kind of react to their environment, do something very basic. And I wanted them to get more and more complex. Ended up getting Dave Cook's book called Robot Building for Beginners, and I built Sandwich, the line following robot, which just has like a comparator chip in it, and it compares like photo resistors to see if there's like a black line underneath them. And it kind of worked. It was pretty good. It was fun. But I wanted it to be smarter. And when I started looking around, if you want your robot to be smarter, your options are become an analog circuitry god or learn to program microcontrollers, which is by far the easier thing, I think. And so I got my first microcontroller, Basic Stamp 2, within like a week or something. I realized how slow that is, and quickly went on to upgrade to like ATtini 13 microcontrollers. And once I started to see the power of those, they really took over my life. And I just kind of learned everything that I could about them. And I have the luxury of not making my living by designing hardware. So I can waste a ton of time learning esoteric things about hardware just because I like it. But whenever I meet people that are embedded engineers for a living, I always ask them, like, what is your background? What did you train in? And almost zero, pretty close to zero, will say, oh yeah, I went to school for embedded systems. Like, it's starting to become a thing now, but most people that are working in embedded systems have come from either an EE, electronics engineering background, or a computer science background, and have kind of learned everything from there. And so what you find is that most of the people that are working with embedded systems have their foot in like every different part of whatever that product is for. So they're involved maybe in some of the circuit design and layout, they're involved in the user experience, they're involved in what the thing looks like, and everywhere in between. And they tend to be one of the first people pulled in when there's a problem that needs solving. And the real question is like, how do you get to the point where you have the experience through everything? And I think it's kind of like a mastery of basic core skills. Let's get back to that argument. The argument you usually see is, you'll see a project that's built with a 32-bit microcontroller, and someone will say, hey, why'd you use a 32-bit microcontroller? You're throwing the book at this tiny, tiny problem. Or on the other side, you'll see someone that has like squeezed every last cycle out of an 8-bit chip, and people would be like, why are you wasting your time? You could have used an ARM chip for that, and it would have been great. The interesting thing about this is 32-bit does bring more to the table. So everything that you could possibly do with a microcontroller is usually packed into those 32-bit devices. There's, some have one feature, some have the other, but really everything that could be on that die is already on there. So why wouldn't you just say, let's get rid of 8-bit controllers and do everything in 32-bit? Now, the counter argument to that I think has a lot of validity is almost everything that we use microcontrollers in is simple. Like 99.9% of the stuff in your life that has a microcontroller in it does like nothing. So if you think about like every electronic thing inside of your car has a microcontroller in it because they're all on CAN bus. So like you press the door lock button and it's not actually connected to the door lock, it's connected to the CAN bus. But the computing power for that is tiny. If you think about children's toys, children's shoes, you have home automation hardware that really is just a simple, basically like a radio bridge to turning LED on and off. So most things don't actually have much computing power in them. It don't need a giant beefy processor. I think there's this kind of valley or this gap in between what 8-bit controllers and simple controllers are really good at, and then where you get to the point where you need like embedded Linux system on a chip. And that's very well fulfilled by that 32-bit, but it doesn't necessarily mean everything should be there with the 32-bit. This is one good example of where you're going to see really simple stuff. This is Sylvania color switching light bulb, and you just screw it in and it changes colors. Kind of boring, I think, to me, but I guess some people really loved it for parties or something like that. But if you cut it open, it's got a really simple circuit inside. That's an ATtini13 microcontroller and 2 RGB LEDs, and it just uses pulse width modulation to scroll through those whenever it's powered up. Really simple application. But I think where 8-bit really wins is it allows you to have the most basic knowledge of what's going on with that microcontroller, because it doesn't have layer upon layer upon layer of features and peripherals and everything that's in there. And I also think that coming from the tool chain, you're looking at a little bit simpler setup. You can actually understand what's going on under the hood with that. Really, what you want to do for a full understanding to become that, hacker by nature for embedded is you want to start with knowing everything about the chip. And so I really say you have to be the master, you have to be the micro Yoda of this. And I think it's a good analogy, because if you look at what Yoda did to teach Luke the ways of the Jedi, he didn't start off, teaching him how to invisibly choke people from one starship to the next. He taught him how to, stack some boxes one on top of the other. And from that basic skill, having that basic mastery, everything comes from that. So of course, the analogy in embedded for that is blinking an LED. So turning on your first LED is kind of a joke, like, oh, you blinked your first LED, but it's really a full stack of understanding. And so if you've put together a project that's blinking an LED, you've proven that you can figure out a power supply, and you can get it hooked up to the microcontroller correctly, and you can get a programmer hooked up to the microcontroller, and you can have a compiler and a makefile and actually do the coding that goes into that. And then on the hardware side of things, like if you just turn on an LED, hey, great, but if you actually turn it on, have it stay on for a little while, turn it off, have it stay off for a little while, then you show that you understand the clock and you understand what kind of cycles are going through that. Now, of course, you can download all kinds of IDEs that take care of this. It's all abstracted out in C, but you actually aren't going to be learning anything about the way that the hardware is actually working by doing that. So if you go with a 32-bit microcontroller, generally you're going to be forced immediately into an IDE. Very few people are programming ARM microcontrollers with a text editor and a makefile that they program themselves. But if you start out with an 8-bit chip, you can totally do that. You can use GCC for many of the 8-bit families. You can write a makefile yourself that is probably 6 lines long. You can write just a basic C file that is, your main.c, which is, if you're just killing cycles with loops, you can probably do that in about 10 lines of code. And it gives you that basic understanding that allows you to kind of move to the next level. I also think hardware debugging is best learned on really simple systems. So this was just I was playing around with 595 shift registers. So I've just got a couple lines coming in on the IDC cable and feeding in clock data and latch onto these. And one of the things that you learn is this pattern of LEDs right here is really bad for troubleshooting, because which side do you think got shifted into that shift register? Going every other one, you have no idea. It seems really simple, but kind of looking at this, going through these exercises and learning, boy, when I need to troubleshoot something blindly, if I can't figure it out, this is not the way to do it. I need to put in a pattern. You can tell which end is which, and you can get a little more data that way. So that's kind of like dead reckoning debugging. But then also, if you look at hardware debugging, which is amazingly useful for embedded systems, almost every 8-bit system has some type of debugging. So like with the Atmel microcontrollers, they have debug wire, one wire debugging for the small microcontrollers, and then they have serial debugging and some other ways for the larger microcontrollers. And again, just with a text file, you can use open source like GDB, or you can go through an IDE if you want to go that way, and put in a breakpoint at any point in your code, and then look at the registers and actually say, what are these registers? Why is this register reading as 0xFF every time I read it, even though it shouldn't be? And I think the thing that's really interesting about that is, like I said, OneArmed embedded at the beginning. So we're tying one arm behind our back here. We're saying let's kind of go down and only work with the small part of this. But if you start from a small system like that, you can actually look at what's coming out of the compiler as assembly. I think it's much more difficult. I haven't found anyone that is writing all assembly for ARM controllers. And I think, having looked at some of the ARM code that I've written myself, it's much more difficult to pick out where your code is, because there's so much happening through the header files and so much happening on the back side of things that your assembler code isn't as easy to parse when you look at it as an 8-bit code is. So you can learn a little bit more about assembly and learn what your C code is actually getting compiled down in if you start with a simpler system. I also think you can read the data sheet on an 8-bit microcontroller. So my favorite kind of go-to is the Atmega 168, and this data sheet's 660 pages. I've read every page of it. I really enjoy it. I know where everything is in it. One of the ARM chips that I like to use is the STM32F405. It's on one of the discovery boards. I've got a bunch of the STM discovery boards. It's a great chip though. The problem is if you download the data sheet for this, it's 200 pages, and then you go and look up like the GPIO registers in there, and it's not in there because they just have another reference manual of 1,731 pages for the entire family of chips. So if you're starting out and you get the IDE set up and you write some basic Blink code and you get it to work on there, that's great. But then when you actually need to go and figure out how do I get this peripheral to work? You just finding it in the data sheet is tough, and actually understanding what you're looking at is even tougher. So, looking at GPIO for instance, so there's a ton of registers on this. So if you look at the mode, like input output, type I think is for alternate types. Speed is an interesting one. So you can actually set the slew rate, like how fast the voltage on these pins is going to ramp up when you turn one of them on. And so if you're doing something that's super high speed, you want to have the slew rate be really high, but then you're going to burn a lot more power that way. So if you're doing low power, you can set that appropriately. There's pull-up, pull-down resistors in it, which is kind of nice. So normally in simpler chips, you're only going to have pull-up resistors. Whenever you have a pull-up resistor, you're going to be draining some current through that, which if you're running on battery is not the greatest of things. And then if you're going to go to sleep, you have to turn them on and remember to turn them back, or turn them off and turn them back on when you wake up. With this, you can set a pull-down resistor. You can set a button and then have that button tie to the voltage rail. That way, you're only sinking current when you press the button. So you're not burning current through a pull-up resistor at all, which is nice. And then there are like a bunch of other data register stuff in there. Alternately, this is for the Atmega 168 or yeah, probably that. There are only 3 registers total for your input and output on an 8-bit microcontroller. So you can read this really easily. It explains it more, but you're looking at a data direction register. You can set things as input or output. Once you have it set as an output, anything you write to this 8-bit port right here is going to show up on the pins. So as far as blinking or turning on your first LED, you can set port B to 0xFF, make all of these outputs, and set your port B register to 0xFF and turn everything on, and it's just going to happen. If you did the same thing with an ARM microcontroller, if you weren't using the peripheral libraries, most likely it wouldn't turn on because you have to do other steps along the way, like get the clock to actually start running. And then I think the gotcha for me when I was first doing an STM ARM chip is you have to turn on the peripheral clock to the actual port that you're using as well. It's a power saving feature, which is pretty nice. But as far as understanding what's going on the hardware, it can be very difficult for someone who's trying to learn the basics of microcontrollers to figure that part of it out. This is one of the registers from that STM chip as well, just to show you how deep some of the features go. They stack everything that they can into these dies, and it's wonderful. So this is a bit set and reset register. So instead of just saying, all right, I want to turn a pin on or off, you can say any of the bits right here, if you set them, are going to make that corresponding pin high. And any of the bits right here, if you set them, are going to make that corresponding pin low. Anything left 0 is going to be untouched. And so at first, it's kind of hard to figure out, like, why would you use this? Why can't you just write to the register? And the thing is, if you want to have some of the pins on the output just remain the same, and it's undetermined what they are, and you want to change some of the others, some of them you want to be 1, some of them you want to be 0, this register allows you to do all of that in a single instruction, because it's only going to change the ones that you set or reset on here, and you can mix them because it's a 32-bit write all at the same time. On an 8-bit microcontroller, there isn't a register like that, so you're actually going to have to read what the current values are, do your logical manipulation to that register, and then write it back to the port. And I think understanding that when you're talking about like syncing things, doing high-speed video and that sort of thing, understanding what the hardware is doing and why you would want to write to this register rather than do a read, modify, write is kind of a really powerful lesson to learn. And so this is a Nokia display that I pull. I had an old cell phone. I'm really bad at getting rid of my old electronics. I don't know if you guys have the same problem, but I end up with a ton of cell phones sitting around. And so one day I was like, you know what? I'm going to see if I can make that cell phone screen work. And I put it on an 8-bit microcontroller, and I was like, hey, I'm going to use the hardware peripherals because this is SPI, and I don't want to bit bang it out. And I started looking into the data sheet. This screen uses 9-bit SPI. So on an 8-bit microcontroller, you can only load 8 bits and you send them out, and the 9th bit for this screen you have to send out separately. So I actually kind of hacked around and added that bit in manually, and then I was like, oh, I'm just going to bit bang this. It was a good learning experience though, because it makes you appreciate, again, those things that a 32-bit microcontroller has. So when you move to ARM, an ARM chip is going to have configurable SPI. It's probably going to have multiple of them, like redundant features on there. And a lot of the ARM controllers, you can choose 6, 7, 8, 9, like usually 6 through 10 bits on your SPI. So all of a sudden I had this like really hacky library on an 8-bit microcontroller. When I moved to an ARM microcontroller on this, I was able to write it all in hardware. It was just a few lines of code to set it up, and then a few lines to push from memory out. The other thing you want to think about when you're moving from an 8-bit to a 32-bit microcontroller is you usually change voltage levels. So 8-bit microcontrollers often will have a range like 2.7 to 5.5 volts. So a lot of people start off in that 5-volt common range and end up buying all of their prototyping hardware. And so I think in itself, it's a good learning experience. I've got a couple of level shifters. So going from 5 volt on one side to 3.3 volt on the other side. So this screen's a 5 volt screen, and then this is a TI Launchpad. This is a Tiva C microcontroller on there. And you know, this is more than just coding now. You're actually looking at like, how do I hook the hardware up? What are the different features on level shifters that I can use? What kind of level shifter is going to be best for this? Is it going to fit the speed that I want to run in? That sort of thing. So again, looking at the benefits of going towards the 32-bit, I think it's you just have all of the hardware options in the world. So if you already understand, you've kind of gone through that boot camp of figuring out how to manipulate registers, how to manipulate bits, then moving up is very empowering, and you actually then have appreciation. Like with that 9-bit SPI screen, you can say having all of the hardware in the world on this chip is wonderful. You're also going to have a lot of that hardware be redundant. So you're going to have like a ton of UARTs. You might get a chip that has 6 UARTs on it. You can kind of go through parametric search and find that sort of thing on it. You also have flexible pin mapping, so you're able to move that stuff around, which is really nice. I think a lot of times the design changes while you're prototyping, and if you have a pin that can change the mapping, you can change it for your next iteration, but still use your current hardware setup for prototyping. DMA is on here twice because it is one of my favorite things. If you've never programmed with DMA before, that should be the first project that you go back and try out. So it's direct memory access. It allows you basically to offload stuff that traditionally would be done in the CPU. You can set up hardware interrupts to call the direct memory access to then load something out of a memory address into your next peripheral. So if you're sending that 9-bit SPI, you can tell it, look, every time you're done sending those 9 bits, pull the next thing out of memory. You could have, you can set it up so you got a user interrupt pin. So whenever somebody presses a button, it automatically loads a new screen, and you can do that all without interrupting the CPU, which is really powerful. If you've heard of the Teensy 3.2, there's a ton of libraries on there that have been written that use DMA for like audio and for video, and allow the user then to just pull in those libraries and do everything that they want on the CPU without having to worry about what's going on in the background. The other thing I really like about 32-bit microcontrollers is they tend to bring in some unified tools. Although I was talking with Mike Harrison last night about this, and maybe it's because I'm using a Linux operating system to develop on these, but I find using a JTAG programmer, I can program almost any family of ARM controllers now. And I wasn't able to do that with 8-bit. So when I was working with 8-bit, I had to have a different controller for PIC and a different controller for AVR and a different controller for STM8. So that's something I value. The OpenOCD has been really great for debugging, so it's on-chip debugging, and almost every board that I've tried to debug with has had a configuration file for OCD already, and there was one that I came across that I didn't. I was able to modify it myself and then submit that back so that it's available for anybody else that wants to use it. And then GCC is an open source compiler, and I would compile GCC for ARM, and it works pretty well across platforms. I think one of the things I ran into is I hadn't compiled it with the right floating point support for Texas Instruments chips, but you can recompile for specific architectures and have those tool chains side by side. You don't need a proprietary tool chain to work with these things. And I think the ARM core is something that I find very valuable. So ARM kind of sets a specification. It's like the IBM of 32-bit microcontrollers. They say you need to have they're actually licensing out the platform to be put in the chips. And what it means is you can expect certain things in hardware. So this bottom layer here is what you can always expect in the ARM Cortex chips. Some of the things that are really nice are like sysTick, so upcounting hardware timer. It's something I almost always implement anyway, and just the fact that it's already in there and already going. It's got really great vector control for interrupts, so you can map how you want your interrupts, where you want the priority, what you want them to do, and there's a ton of them. There's great support, like I said, for debugging. And when you go up a little bit more, so this SeamSys core is like a peripheral standard, an API standard that you can expect to work for all the chips. So on kind of a really high-level, hand-wavy platform, you can say, all right, I've got these features that I always want to implement when I start a new project. You can kind of expect them to work through that. And then there are a lot of higher-level features too. So if you're doing DSP or you need a real-time system, you can lock into some of these. So it's a lot more uniformed across different architectures and different chips within families just because of this standard. When I look at this argument of like, hey, you should have used a 32-bit controller, you should have used an 8-bit controller, I really think that buying into it is the wrong thing. It's a stupid argument to have. So a good friend of mine who I've known for years, fantastic carpenter, makes great custom cabinetry, builds houses. But when he's come over to help out with projects, he doesn't just bring a hammer. He has a nail gun, and he uses both. He can hammer a nail in 2 shots when he needs to, but when he's reshingling an entire roof, he uses a nail gun. At the same time, if he's going to reach for a circular saw and you're going to do a corner cut with the circular saw, because of the the curve of the blade, you can't finish that corner. So he's got a handsaw to finish that. He wouldn't come over and say, I'm not going to use a handsaw because it's old. He would have all of those tools in his toolbox, and I think we should too. You shouldn't say, I'm not going to use one architecture or the other because you think one is older or one is newer. I think a really great example I had recently, I went and participated in a weekend-long KiCad workshop that Anul Mahadharia was hosting at Nova Labs. And I wasn't really prepared, I guess. I didn't think to myself, oh, you're going to do a circuit layout workshop, you should have a circuit in mind. So all of a sudden I had to come up with an idea like on the spot. And I've always wanted to do a spinning persistence of vision display. And so I very quickly thought about what parts I would want to use. I chose these APA 102 RGB LEDs, which are basically SPI driven. And I thought, okay, how fast is this going to spin? How many bits am I going to have to push out? And I calculated my clock speed, and I'm like, oh, 20 megahertz is going to be fine. I'll throw my favorite ATmega 168 on there, and we'll be fine. Until I actually got it and populated it and started coding and realized I don't have enough RAM on this thing. So it's got 17 pixels, 24-bit color, spinning. If you do one slice every degree, you've got 360 degrees per frame, and it's something like 18K of RAM. And so I put this little 8-bit controller on here. It's got plenty of speed, but it's only got 2K of RAM. So I'm really short. So then you're looking at, can I sacrifice some of that speed to do lookup tables so that the 20, I don't have, I can store a frame in RAM and not run out of memory so quickly. The sad thing is on this one-off prototype, I only got enough parts to do 3 of these. I think I have 10 boards, I have components for 3 of them. This chip's about $2.50. If I'd gone to that STM32F405 chip that I've been showing data sheet stuff from, that would have been about $7.50 more per board. And so that sounds like, why would you ever add that to the BOM cost? But for the prototype, it would have been a lot smarter for me to start off with that chip, prototype it like this, figure out what all the problems were, and then decide if I can go to a less expensive chip if I wanted to make more of them. As it is, I saved $7.50, but now I have a board that I can't really do my full programming on. So my options at this point, I figure, are I don't think you can find a direct pin replacement for a controller that has at least 18K of RAM. I mean, that STM chip would have, I want to say, over 100K of RAM in it. That might not be quite right, but it's got plenty at any rate. But I don't think it's a direct pin drop-in. So now I'm going to have to, either like glue a controller onto this board and patch it in, or respin the board. So this is just one example, and I think really, the answer is we should be prototyping with 32-bit, and then boiling down what we need from there. Rather than going the other way where I figured out I started with a smaller chip and I can't use it. But the caveat is you have to understand the universe of embedded before you can go up to that 32-bit, because everything is so abstracted and everything is so hidden that it's not going to be a full control of the hardware experience. It's mostly going to be an abstracted coding experience. Thank you.